In this video, we're going to compare means from two samples, and in this case, we're looking at independent samples. So the definitions for independent and dependent samples. We have independent, which is what this video is about. The two samples are not matched or paired. A key indicator if you're trying to decide if you have independent or dependent variables, if the two sample sizes are not the same, it has to be independent. But keep in mind that n1 can equal n2. The two sample sizes can be the same even though they're not paired. In a dependent sample, the two sample sizes have to be the same because you have matched or paired samples. So something in the first sample matches with something in the second sample. So I have examples here. You could do before or after. So maybe a pre-test and a post-test. You could have twins in a study where one of the twins is in one group and the other one is in another group. You could have couples being split into the two groups and they'd be a pair between the two groups. So again, this example is going to be looking at independent samples. If the two sample sizes are not equal to each other, it has to be independent, but independent can have the sample sizes be equal. A bunch of notation here for setting up problems. We have the mean of the two populations using mu1 and mu2. The population standard deviation for the two would be sigma 1 and sigma 2. The two sample sizes, n1 and n2. The two sample means would be x bar 1 and x bar 2. Put subscripts on those. And then S1 and S2 for the sample standard deviations. So we have requirements. Again, you should check this at the start of every problem. The population standard deviations are unknown. We only know the sample standard deviations, which are S. The samples are independent, which I talked about earlier. They both have to be simple random samples, and you have to check, is the sample size greater than 30? If it is, then you're good. If the sample size is not greater than 30, then it should say somewhere in the problem that they have normal distributions. Following this in your notes, there's all the equations that you would use, but again, we're just going to look at how the calculator will solve these for us. So the next thing we'll look at is the example. So in the example, we have a clinical trial for testing treatments of chronic coughing. We have 100 total participants, and they're going to be put into two groups of 50 people in each group. We're looking at coughing episodes per hour, and we have mean and standard deviation for the first group. So, and these are from a sample. So the sample mean of the first group and the sample standard deviation is from the first group. And then the second group, we have a mean for the second group of 1.21 and a standard deviation for the second group, which would be S2. It's asking if the two groups are significantly different, and it gives us a value for alpha. So up here, there's 50 people. Both groups have a sample size of 50. All right, so requirements. We need simple random samples. And it doesn't say if the 100 participants were selected randomly, but they were randomly assigned into the groups. So we can assume that they're simple random samples. Second requirement is we don't know anything about the population standard deviations. That's true. All we have is sample standard deviations. Third requirement is we need independent groups. So the first group and the second group need to really have nothing to do with each other. And that's true in this case. It doesn't say anything in the problem about having pairs or partners or anything like that between the two groups. It's not a before and after. It's not a study of the same person with and without a treatment. So the two groups are independent from each other. So they do have the same sample size, but that doesn't make them dependent necessarily. It's whether or not there's any pairing or matching between the two groups. Last requirement, sample size greater than 30 for both. Both groups have 50, so we are okay on that. So summarize the data. I kind of did that as we went through, but N1 is 50, N2 50. Sample mean for the first group is 0.97. Sample mean for the second group is 1.21. Sample standard deviation for the first group 0.41, and for the second group 0.37. It says significantly different, so we're going to use a two-tailed test, not equals, and it tells us alpha is 0.01. So there's all the information from the problem. And let's write some hypotheses. When you're doing two means, we're going to say either that the two population means are equal, or you can write it as the difference of the two means is 0. There's no difference. In the alternative hypothesis, we're using a not equals because it says different in the problem, which would make the difference not equal to 0. So there's your general setup for the problem. After this, we have 3 methods that we can use. We can use the p-value method, critical value method, or confidence interval method. I'm only going to show the p-value method and the confidence interval method because those are the 2 most common ways to solve the problem. So the p-value method we'll do first. Save that. Okay. So we have calculate a test statistic, and when we're doing samples, typically we use t unless you know something about the population standard deviation, which we do not. So the equation for t will give us this. In the null hypothesis, the difference between the 2 population means is 0. So that's what we're going to plug in for that one. Right. Again, if you're doing problems like this with your calculator, do the parts and keep all the parts separate as you go. It'll reduce the errors that you make. So there is our value for t, negative 3.07. What you would do to get a p-value is then use the t-table In the t-table, all the values of t are positive, so we're going to do the absolute value of this and use t equals 3.07. And the other thing you need in order to look up p-values in the t-table is degrees of freedom. And when you're doing independent samples, you use either n1 minus 1 or n2 minus 2, whichever is smaller. In our case, they're going to be the same because the sample sizes are the same. So we want to use degrees of freedom of 49. In the table, there is no row for degrees of freedom 49, so you'd use the next smallest. Which on the table is degrees of freedom equals 45. Okay. On the table then, again we'll look at the table during class together. So if t is 3.07 and we're going across the row of degrees of freedom 45, what you'll see is that our t that we calculated, the test statistic, is greater than the t in the table of 2.690. And then if you go up to the top of that, the p-value that corresponds to 2.690 is 0.01. So our p-value must be less than that. Since our t is bigger than the critical t that's on the table, our p-value is less than 0.01. Alpha in this problem was 0.01, so our p-value is less than alpha. And we'd reject the null hypothesis. The null hypothesis was that our two groups are the same, so our conclusion would be that the two groups are different. So they're not, the two treatments that they're studying are not equally effective. The two groups had different results. Okay. So we're going to see how our calculator will solve this problem on the next page. So here's the instructions for the Twosample Ttest in your TI-83. We have under the stat menu, going to tests, and we're doing 2 samples with means, so that's a Twosample Ttest. In your calculator, you'll be able to choose data or stats. If you had 2 lists of sample data, then you would use data. If you're just given the mean and standard deviations in the problem, then you use stats. So I'm going to go over to stats. And it's going to ask for the 2 sample means and the 2 sample standard deviations and the 2 sample sizes. So our first sample mean was 0.97. The standard deviation for the first group was 0.41. Sample size for the first group is 50. And then for the second group, we had 1.21, 0.37, and 50. We want the sign from the alternative hypothesis. It was asking if the two groups are different, so we'll use not equal to. It's going to ask you if you want the pooled standard deviation. There's a little bit of discussion in your notes about the pooled standard deviation. It's not commonly used, and some statisticians advise against it. So we're always going to choose no for pooled. And then we calculate. So there's our test statistic t, negative 3.07, same number we got using the equation. P-value of 0.0028 if you round it. It's more accurate than what you can do with the table. We actually have a number to report for the p-value and not just a number that the p-value is less than. But still, the p-value is going to be less than alpha. You'd get the same conclusion. So since our p-value is less than alpha, reject the null hypothesis. All right, two other methods. We have critical value method and confidence interval method. Just a quick thing about the critical value method. If on the table you could look up the critical value of t for degrees of freedom equal to 49, and you'd have to use 45 on the table, and alpha is 0.01. The number in the table for t is 2.690. Our test t, if you take the absolute value, was 3.07, and since our test t is bigger, reject the null hypothesis. Okay. So you'd have to do your calculation for t in order to get that, and then look up your critical value of t in the table. If you're getting the t from your calculator, you're also getting the p-value anyway, so you may as well just do the p-value method. So we're not going to spend a lot of time on the critical value method. But let's take a look at confidence interval. For a confidence interval, the equation that we have is a critical value of t and then plugging in the standard deviations and sample sizes. The critical value of t is 2.690. When you plug in all the numbers for s and n into here, I'm not going to write it all out, but so this is the t, and all of this ends up being this number. So e is 0.21 when you multiply those together. And to get your confidence interval, take the difference of the sample means plus or minus the margin of error. And we get negative 0.24 plus or minus 0.21. So the smaller one, negative 0.24 minus 0.21, would give you negative 0.45. And negative 0.24 plus 0.21 gives you negative 0.03. Okay, so to interpret a confidence interval, for the sake of making a decision about something, if the difference is not equal to 0, you reject the null hypothesis. So since 0 is not in this confidence interval, we have to reject the null hypothesis that says the difference can be 0. And we can say there is a difference between the two treatment methods. For coughing. Okay. So your calculator will also calculate a two-sample t interval. So in the stat menu, going to tests, we have to arrow down until we find two-sample t interval. Again, you can choose between data and stats. So if you had lists of data, you can use data. We have stats, so we're going to use that. And all our numbers are saved in here from when we did the test, so nothing's changing here. Put in the confidence level. Since alpha was 0.01, the confidence level we need is 0.99 because I have to add up to 1. We're always going to choose no for pooled, and we hit calculate, and there's our confidence interval. Negative 0.4452, we got negative 0.45, to negative 0.0348, and we got negative 0.03. So same interval. The calculator is a little bit more accurate, but that's doing the same process as we used with the equation over here.